So we are done with the first module of the course Microwave Engineering, which was Introduction to Microwaves. What we studied: single stub, double stub matching, mainly impedance matching networks. We studied something about strip line and microstrip line design, and coupled lines was given as self-study. So let's start with the second module, which is waveguides. So what are waveguides? As the name suggests, they are nothing but guiding structures. What do they guide? They guide waves. And which wave? Obviously, electromagnetic wave they will guide. Right? So how they guide? Very simple example is our coaxial cable. What is the construction? It has a center conductor separated by a dielectric. Then you have a outer conductor. Right? So this, what does it do? Between the two conductors the current is passed and we get a transportation of signal. So this is one form of waveguide. It is which type of waveguide? It is a metallic waveguide. But what happens in metallic waveguides? They are applicable only for frequencies from kilohertz to few gigahertz. As the frequency increases, what will happen? Losses will increase. So this cannot be used at very high frequencies. So for that, which waveguides are used? Usually hollow dielectric waveguides are used. So when our hollow dielectric waveguides are used? When we are not requiring very high losses. So when we have very high frequencies, we use dielectric waveguides. Right? So what are those type of waveguides? They are simple rectangular waveguides and circular waveguides. Both are hollow. Right? So they are separated by a dielectric, which is usually air. Okay. So these are the two type of waveguides we study in this module. We will not go for circular because it is very complicated. So we'll just leave that so we'll study about rectangular waveguide mainly in this module, and then we'll go to other passive devices which are resonators, isolators, gyrators, circulators. So first thing is about waveguides. So before actually going to rectangular waveguide, we'll study a general form of waveguide which is called as parallel plane or parallel plate waveguide. So we have studied a topic in electromagnetic engineering. What was that? Reflection and refraction from surfaces, right? So we'll use the same thing here. This is my z-axis and this is my x-axis. Okay. So I am making a wave, electromagnetic wave incident from a medium 1 to medium 2 in this direction towards the origin. So what will happen? And let's say I am saying this is conductor. Sorry, this is medium 1, this is medium 2. So since this is conductor, what will happen? We have studied in our electromagnetic course that conductors will reflect the electromagnetic wave. The electromagnetic wave cannot penetrate a conductor. If you remember, we had taken the example of a metallic tiffin. I had brought a metallic tiffin to the class and demonstrated it. So what will happen? It will get completely reflected in this way, right? And let's say we are studied two types of polarization also, perpendicular and parallel. What was perpendicular polarization? Electric field was perpendicular to the plane of incidence. So what is my plane of incidence now? The paper itself is my plane of incidence. So I am assuming what? Electric field is perpendicular polarization. That is, electric field is perpendicular to the plane of polarization. So this is my incident electric field EI, and wave is traveling in this direction, right? So this is the direction, like this. So E to H will be what? Curved fingers, my curled fingers, right? So H will go in this direction. So this is my HI. Similarly here it is going upwards. So again it is perpendicular polarization. So we'll say ER is in this direction. So again curled fingers tell me what? That it is towards HR is towards right. Right, and this angle is theta. So both angles are theta. Angle of incidence is always equal to angle of reflection. And my y will obviously be coming outside. We use right-handed coordinate system. We studied in first lecture of electromagnetics. So this is my complete diagram, right? So next step is what? To find the electric field E1 for medium 1 and magnetic field H1 for medium 1. So we'll not derive it. I'll give you directly. It is not part of the syllabus, but for understanding waveguides, it is very important. So I'll just write it directly. Again, the derivation is not there. So this lecture is just for understanding. It will not be asked in the exam. Simple. First 2-3 lectures of waveguide. So it is given by 2j ei naught sine of beta 1x cos theta e raised to minus j beta 1z sin theta y cap, and h1 is I'm just referring from the book. So it is 2j ei naught by eta 1 sine of beta 1x cos theta e raised to minus j beta 1z sin theta cos theta x cap plus 2 ei naught upon eta 1 cos of beta 1x cos theta e raised to minus j beta 1z sin theta into sin theta z cap, right? So this is E1, this is H1, right? So now let's start to analyze the waveguide, right? Again, you don't have to remember these equations. First 2-3 lectures are for understanding purpose only. In fact, parallel plane waveguide is not part of the syllabus, but for understanding rectangular waveguide, we are studying parallel plane waveguide. It is not a part of syllabus. So what we are analyzing? We are analyzing a waveguide, right? So let's say this is the electric field Ey. It is given as volts per meter, obviously, unit, and H1 is amperes per meter, right? So I want to check what happens when the electric field goes to 0. So what will happen when electric field goes to 0? That is, I equate this to 0. These are constants, so this will go away. This is e raised to j term, so we are not interested, and this is vector. So what remains? Only sine of beta 1x cos theta, right? So sine of beta 1x cos theta equal to 0. So what will happen? When will it be 0? When beta 1x cos theta will be what? M pi. So beta 1x, cos theta equal to m pi, right? So what will be the value of x? Let's say it is equal to d. So it will be what? M pi by beta 1x. Am I correct? Cos theta. X will not be there, x is here. And what is beta 1? It is nothing but our phase constant. So 2 pi by lambda 1. It is corresponding to medium 1. That suffix is indicating that. So 2 pi by lambda. So lambda 1 will come here. Pi will get cancelled. So m lambda 1 by 2 cos theta. It is exists for values m equal to 0, 1, 2, etc. Right? So this is my x. So again, what is the significance? This x is, what is it giving? When electric field at these values of x, electric field goes to 0. Which electric field? This electric field. Means what? Now I have this x equal to 0 indicates this. This is x equal to 0. That is what I am drawing here now. This is my z axis. It indicates x equal to 0. This is my x axis. Right? So I'll use a brown pen to indicate x equal to 0. What does this indicate? If I go a distance d from x equal to 0, such that the electric field becomes 0, what will happen? I go a distance m lambda 1 by 2 cos theta. So m equal to 0 gives me a distance x equal to 0 only. So let's take m equal to 1. What am I getting? Lambda 1 by 2 cos theta. So I go a distance d. This distance is d. And what is it? Lambda 1 by 2 cos theta. What is happening? The electric field is 0 here. So it will be 0 again here. If I go further distance, m equal to 2. So 2 lambda 1 by 2 cos theta. That is lambda by cos theta. So lambda 1 by cos theta, if I go another d, what will be? Again electric field will be 0 here. Right? Means what these equations are telling us, again what I say in the class is, don't see the equations. See the mathematical equations as concepts. Don't see them as mathematics. See them as concepts. So these equations are telling us, if you have a conducting boundary at x equal to 0, you go a distance d such that it is equal to m lambda 1 by 2 cos theta, where m equal to 0, 1, 2. What is happening? You encounter another boundary at which the electric field is 0. And that first distance is lambda 1 by 2 cos theta. You go further distance d, that is you further add lambda 1 by 2 cos theta. What will you get? Lambda 1 by cos theta. At all these boundaries, even if you place a conducting boundary here, are the boundary conditions changing? They are not changing, because the electric field is 0. Right? Means what am I getting? I am getting a closed structure, bounded structure now. What was happening initially? I had only one conducting boundary. So if I was sending an electric field or electromagnetic wave, to be precise, it was coming here, bouncing here, going like this, and it was getting away. Nothing was happening further. Right? But what will happen now? Since we have placed, let's say I have placed one more boundary. So this is x equal to 0, this is x equal to d. So I have now a bounded structure. Of course, it is infinite in this way. Along horizontal way, it is infinite. So if I somehow make a electromagnetic wave incident, what will happen? Since this is conductor, it will get reflected. Since again it encounters a conductor here, it will get reflected from here also. And this way, I will get a what? Propagation of the electromagnetic wave. So what is this? This is what we have made a waveguide. And since this is infinite along the z-axis, it is called as what? These two lines are parallel. So it is called as parallel plane waveguide. Why waveguide? Because it is guiding the electromagnetic wave. So this is the first simple waveguide which we have devised from simple equations. Again, see the equations as concepts. Okay. So this is the first thing we understand from these equations. This is the first takeaway. Now let's just find cos theta from this equation. So what will we get? We get that cos theta equal to m lambda 1 by 2d. So again, if I write from here, what will it be? M pi by beta 1 d. So m pi by beta 1 d. Right? Now what does this imply? First, what we said, we had only one conducting boundary. So we are not getting any propagation of electromagnetic wave. But when we introduce one more boundary, obviously with the condition x equal to d, which is corresponding to this equation, if only if this condition is satisfied, the electromagnetic wave will propagate. Right? This was the only thing. But what we are getting, if we just interchange this, that we cannot have the wave propagation at all angles. Right? Theta is what angle? It is this angle. You are making it incident with respect to a normal. So you cannot have all the angles. Why you cannot have all the angles? Because this is a discrete value. Not this, sorry. M is a discrete value. What is the value of M? M equal to 0, 1, 2, etc. Right? So if M is 0, theta is pi by 2. If M is 1, you will get some value. M is 2, you will get some value. So you are not getting all infinite values of theta. That is, theta is not going from 0 to infinity, encompassing all values. So what you are having? You are having discrete angles of theta. That is what I mean. Means we cannot launch the waves at any arbitrary angle. Simple. Right? So cannot launch waves at any arbitrary angle. That is what we understand from this equation. Right? So next, what we understand from this equation. So there are 4 points we get. So first point is we migrate from continuous domain of theta to which domain? To discrete domain. That is what? That is, we have finite angles of theta to launch EM wave. Right? That is what, whatever I have written in brackets is the meaning of the first point. Next, what we understand? Since cos theta is less than equal to 1, cos theta is less than equal to 1, it is not having values from 0 to infinity. It will always lie between -1 and 1. But we will take, let's say, positive values only, 0 to 1. So what will happen? There are, first thing we said, there are discrete angles. All angles will not be encompassed. Now what we say? There are finite number of angles. There will be finite number of angles. Here we said it is not continuous domain. But we didn't talk about infinite angles or finite angles. Though I have written in, so this is actually the second point. I can see there are finite number of angles for a given boundary separation D, right? And frequency. Now why and frequency? Because I have a boundary separation D, and if I take beta, what will I get? Beta is 2 pi by lambda 1. So lambda is C by F. So I get frequency also. Next, third point. What if D is less than lambda 1 by 2? If D is less than lambda 1 by 2, what will happen? So lambda 1 gets cancelled, 2 gets cancelled. So M cannot be greater than 1. So M is 0 or 1 maximum, right? What does this imply? This implies that no wave can be launched. No wave can be launched between what? The two conducting planes. Why no wave can be launched? Because cos theta cannot be greater than 1. So if you take D is less than lambda by 1, for example lambda 1 by 4, so what will this be? M lambda 1 upon 2 lambda 1 by 4. So lambda 1 gets cancelled. So M, this will be 2M. Right? So you are getting cos theta, and let's say M is 1. So you are taking the smallest value of M apart from 0. So cos theta equal to what? If M equal to 1, cos theta is 2. Is this possible? Never possible. So you cannot have D1 less than lambda by 2. Okay. So if D1 is less than lambda by 2, cos theta greater than 1, so you cannot launch a electromagnetic wave at all. So again, this is a condition, right? And finally, if you increase D, that is if D increases or lambda decreases. So if D increases, what will happen? Cos theta will decrease. So if 2 pi by lambda or lambda decreases, what will happen? Again cos theta will increase. So if you either decrease D or you increase D or you decrease the lambda, that is wavelength, or in other words increase frequency, what will happen? Cos theta will decrease. What does this indicate? Just think for some time. Cos theta is decreasing, right? If D is increasing, cos theta is decreasing. D is increasing means what? The separation between the boundaries. These are the two conducting boundaries. We have bounded the structure. If this distance is increasing, what will happen? Cos theta will decrease, right? Means you will come more less than 1. Means what will happen? The number of angles which you will have will go on increasing. This is what it means. So the number of angles at which the wave can be launched can be increased by increasing the separation or by decreasing the wavelength, or in other words increasing the frequency. So these are the four takeaways from this single equation. Okay, so again I have proved that see the equations as concepts and not mere mathematical equations. Okay, so now let's do some mathematics. So let's take even and substitute cos theta. What is cos theta? Cos theta is m lambda 1 by 2d, which is equal to m pi by beta 1 d. So what will be even? Let's see. I have written even somewhere. So this is my even. So what will be even equal to, if I substitute cos theta, 2j ei naught sine of beta 1x, and let's substitute cos theta as m lambda 1 by 2d. So m lambda 1 by 2d e raised to minus j beta 1 z. It is sine theta. So what will be cos theta? Square root of 1 minus cos square theta. So 1 minus m lambda 1 by 2d the whole square y cap. Similarly, you can write h1 equal to, this is vector. This is also a vector, sorry. I always stress on these points, but I only forgot this time. So this is h1 also, you can write in the same way, right? Not is by beta 1x m lambda 1 by 2d. Let's try to simplify this. So beta 1x m lambda 1 by 2d. What will it be? Beta 1 is 2 pi by lambda 1 into x into m lambda 1 by 2d. So what will you get? These two gets cancelled. Lambda 1 gets cancelled. So what do you get? M pi x by d. So m pi x by d. Right? And we can write, now what is happening here? Usually you have what? If a wave is traveling in plus z direction, you have e raised to minus j beta z. What you are getting here? E raised to minus j beta 1 z into some constant. M lambda 2d once decided are constants. Right? So this is a part of sort of beta only. So what we can say? Beta equal to beta 1 square root of 1 minus m lambda 1 by 2d the whole square, and this is nothing but what? Beta 1 sine theta, because we had written this as square root of 1 minus cos square theta, right? So what does it imply? Sine theta equal to beta upon beta 1, right? So what we can say finally? Therefore the fields between the conducting boundaries are. So we'll write even vector. So I'll use a new page for some reason. We'll come to know why. So this is even vector equal to. So if you solve it completely, we'll get 2j ei naught sine of what we have written. Beta 1x m lambda 1 by 2d is m pi x by d. So 2j ei naught sine of m pi x by d e raised to minus j beta 1 sine theta. So beta 1 sine theta z, and we are writing it as beta, right? So sine of m pi x by d e raised to minus j beta z y cap. Similarly, we'll write h1 vector. You have two components, so 2j ei naught sine of m pi x by d e raised to minus j beta z m pi by beta 1 d x cap plus 2 ei naught upon eta 1 cos of m pi x by d e raised to minus j beta z beta upon beta 1 Z cap. So these are our final equations for electric field and magnetic field for the parallel plane waveguide. What is the condition? It is perpendicular polarization. Okay. So what happens further? That we'll see in the next lecture. So it is a suspense. So just think over it what these equations mean. Okay. So again, make sure you think over it, and if you find that you are correct, you will be very happy. So make sure you think over it. This is the way you should study, as I tell in the class.